Bismillahirrahmanirrahim. In this lecture, I am solving problem 2.10 from the book Power Plant Technology by Al-Wakil. So the statement of the problem is a Rankine cycle operates with inlet steam at 75 bar and 320 degrees centigrade and given data initial pressure entrance to the turbine, inlet steam mean exit of the boiler and inlet of the turbine, which is 75 bar, and 75 bar is equal to 7.5 megapascal. If you convert bar into megapascal, divide it by 10, and temperature T1 is equal to 320 degrees centigrade. Condensing at 50 degrees centigrade and generates 250 megawatt of power. Condensing temperature T of condensation is equal to T3 is equal to 50 degrees centigrade and generates power. Total power generated and the cycle is 250 megawatt. The cycle features a single stage of reheat that returns the steam to and reheating. There are first expansion in the boiler, and then after expansion again we reheat it. There is a single reheat stage, single reheat stage in the condenser in the turbine, single reheat stage. So after reheating, the temperature is again increased to 320 degrees centigrade, and a closed type feedwater heater receives bled system at the reheat pressure and cascades the drain back to the condenser. The high pressure turbine has a polytropic efficiency of 91%. Efficiency of high pressure turbine is equal to 91%, which is equal to 0.91, and efficiency of low pressure turbine is equal to 93%, which is equal to 0.93. The pump operates isentropically. It means that entropy is constant in the pump. Calculate the mass flow rate of the steam at the turbine inlet in kilogram per second. Required is find mass flow rate of the turbine. For B, the cycle efficiency and the cycle work ratio. Cycle efficiency and work ratio. And the terminal temperature difference is equal to 2.5 degrees centigrade. Now we start solution. Let me explain first the Rankine cycle with a single reheat. Temperature in degree centigrade and entropy in kilojoule per kilogram per Kelvin. This is the saturation curve, and in the turbine first pressure is increased to pressure is uh, 75 bar and temperature is 350 degrees centigrade. Now in second, this is the expansion in the turbine. This is the expansion in the turbine from 1 to this is, let's suppose, 2s, and in real condition this is something like this. This will be like curve. This is 2, and after reheating again to the after reheating again to the 320 degrees, temperature will be same at these two points. This is T1 is equal to T1 dash, which is equal to 320 degrees centigrade, and at point 1 pressure is equal to 75 bar. P1 is equal to 75 bar. P1 dash pressure is not given to us. We will suppose this pressure. And now again it is expand up to point 2 dash. And here this is 2 stage, and the real value is something like curve 2 dash, 2s dash and 2 dash. And now this is expansion in the condenser. This is condenser uh, heat rejection in the condenser from 2 to 3. This is point 3. From point 2 to 3, this is the pump work, and then this is expand to and boiler. This is heated and boiler, and steam is generated from point 4 to 1. And here it is again cascaded to condenser. So this is the TS diagram for the problem. Now to find uh, the cycle efficiency, to find the mass flow rate, and to find the work ratio, first we have to find enthalpies and entropies at different points. So then with the help of different formulas we can find the net work done, work of turbine, work of pump, at different work of high pressure turbine, work of low pressure turbine. So with the help of all these values we can then find the required values. So we are starting the solution with the help of diagram. So first we know that as at pressure is equal to 7.5 megapascal. T1 is given to us as 320 degrees centigrade, but saturation temperature is equal to 290.54 degrees centigrade. As this is from saturated steam table, as T1, which is given to us 320, is greater than Ts, so point 1 is in superheated region. Point 1 is in superheated region. Now we will use superheated steam table. So from superheated steam table, at pressure P1 is equal to 7.5 megapascal and T1 is equal to 320 degrees centigrade. Point H1 and point S1. So if we check the superheated steam table, this is 7.5 megapascal, and at 7.5 megapascal 325 degrees centigrade and 350. So to find H and S we will interpolate between 325 degrees centigrade and 350 degrees centigrade. So pressure P1 is equal to 7.5 megapascal is available in table, but temperature is not available. Temperature at degree centigrade and superheated steam table 300 is available and 325, and we have to find at 320. So we will interpolate. At 300 degrees centigrade, enthalpy is 3839.8. At 320 degrees centigrade, 2935.5, and at 320 we have to find enthalpy. Now entropy at 300, entropy is 5.9335 is 1 and 6.090. Now interpolate for H1 and S1. So H1 is equal to, after interpolation, H1 is equal to 2916. I already explained interpolation in the previous problem. Kilojoule per kilogram. And S1 is equal to 6.090 0.0643 kilojoule per kilogram per Kelvin. Now we have to find enthalpy and entropy for after reheating at this stage. I find H1 at this stage. Now I have to find H1 dash and S1 dash for this point after reheating. So after reheating, temperature is given to us 300 degrees centigrade. As after reheating, temperature T1 and T1 dash are equal, which is equal to 320 degrees. But we will assume pressure. So after reheating, the pressure must be 20 to 30% of the boiler pressure. So 24% of the boiler pressure 24% of the boiler pressure is 18 bar, which is equal to 1.8 megapascal. It means that we will assume pressure 1.8 megapascal per reheating, but there is a problem. But in our case the reheat pressure is also bleed pressure in our problem. Bleed means exit of the turbine. Bleed means exit of the turbine. So this is bleed pressure mean at this position here at this position. And if we check the saturated steam table at 1.8 megapascal, at 1.8 megapascal, the saturation temperature is 207.2 degrees centigrade, which is too much at the exit of the turbine. It means that at inlet of the turbine temperature is 320 and exit it is 207, but this difference is too small and 207 is too much temperature here. It means that we will assume pressure in reheating less than 1 megapascal and so pressure in reheating P1 dash is equal to 0.8 megapascal. You can assume it as 0.9 or 0.7. So here we assume it 0.8 megapascal. Now we are finding the entropy and enthalpy at 0.8 megapascal and 320 degrees centigrade. Now and if we check at 0.5 megapascal, 320 is superheated temperature. So we will use superheated steam table. So from superheated steam table, at pressure P1 is equal to 0.8 megapascal and temperature T1 dash is equal to 320 degrees centigrade. Again 320 is not available in the table, so we will do interpolation. So this is temperature in degree centigrade, and in this region if we check 300 and 350 are available here. If we check this video 0.80 megapascal, so here 300 and 350 are available, so we will interpolate between 300 and 350 degrees centigrade. So temperature in degree centigrade, H1 dash in kilojoule per kg and S1 dash in kilojoule per kilogram per Kelvin. So temperature 300 and 350 are available, and we have to find the value at 320 degrees centigrade. So at 300 degrees centigrade, enthalpy is given in the table 306.9, and we have to find H1 dash. At 350, enthalpy is 3162.2. So similarly, entropy is 7.2345, and here S1 dash is required, and at 350 degrees centigrade this value is 7.4106. So do interpolation and find H1 dash and S1 dash. So these values are H1 dash is 3099.02 kilojoule per kilogram, and S1 dash is equal to 7.30 kilojoule per kilogram per Kelvin. Now we have to find H2 enthalpy and entropy at this stage. Here H2 and H2S, we have to find the enthalpy here. So here pressure is same 0.8 megapascal. So at this pressure we will find, and this is in the wet region, this point is in the wet region, so we will use saturated steam table to find the enthalpy and entropy H2S and H2. So first we check whether this font is in. So is from saturated steam table at pressure is equal to 0.80 megapascal. Sg at this point, SGS from the table is 6.6615, and we know that S1 is equal to, here entropy is constant, S1 is equal to S2 or S2S. S1 is equal to S2S. S1 is equal to S2S, which is equal to 6.0643 kilojoule per kilogram per Kelvin, as S1 is less than Sg, or S1 is equal to S2S. S2S is less than Sg, so 0.2 is in wet region. So we will use a saturated steam table. So from saturated steam table at pressure is equal to 0.8 megapascal. 0.8 megapascal is also the exit pressure of the turbine. This is already explained. I explained previously. So therefore I use here 0.8 megapascal. So here if I check steam table, so HF is equal to 721.02 and Hg is equal to 2768.3. Similarly, SF is equal to 2.0460. Unit is kilojoule per kilogram. Here unit is kilojoule per kilogram per Kelvin, and Sg is equal to 6.6615 kilojoule per kilogram per Kelvin. So now we have to find H2S. So but for H2S first we find X2S. So as S2S is equal to SF plus X2S into SG minus SA. Putting values in this and find X2S. S2S is equal to 6.0643. S1 is equal to S2S. SF is equal to 2.0460 plus we have to find X2S and SGS 6.6615 minus SF is equal to 2.0460. So here only X2S is unknown. So solve this equation and find X2S, which is equal to 0.87. Now you can easily find H2S. H2S is equal to HF plus X2S into Hg minus HF. So H2S is equal to, the value of HF is 721.02, X2S is 0.87, the value of Hg is 2768.3 minus the value of HF is 721.02. So simplify this and find the value of H2S. Exit of high pressure turbine or an ideal enthalpy. So this is 2502 kilo. Now we can find uh, actual enthalpy. So efficiency of high pressure turbine is equal to H1 minus H2 divided by H1 minus H2S. Efficiency of high pressure turbine is given to us as 0.91. H1 is equal to 2916.3, 2916.36 minus H2 is required. H1 is 2916.36 and H2 is 2502. So H2 is equal to, simplify this equation and find H2, which is 2539.298 kilojoule per kg. Now work of high, now we can easily find work of high pressure turbine, H1 minus H2. This is simply we can, this is H1, this is H2. So H1 minus H2 is work of high pressure turbine. So work of high pressure turbine is a H1 minus H2, which is equal to 2916.36 minus 2539.298. So work of high pressure turbine is equal to 377 kilojoule per kg. Now temperature of feedwater outlet. We know that terminal temperature difference. What is terminal temperature difference, which is given to us in the problem? It is equal to temperature of steam condensing, minus temperature of feed water outlet. So temperature of feed water outlet will be equal to temperature of steam condensing minus TTT. So temperature of steam condensing is 170.41 minus TTD is given to us 2.5, and you can find this temperature from 0.8 megapascal. This is saturation temperature. It is given in the steam table. So temperature of feed water outlet will be equal to 167.91 degrees centigrade. Now we are finding the pump work. So in the problem 2.2, I explained the formula for work pump is del P into Vf, del P into Vf. I can write this as pressure, high pressure minus low pressure at 50 degrees centigrade. Pressure at 50 degree. Pressure at high temperature at 320 degrees centigrade. And pressure and low, because in pump pressure increases from low to high. In the pump the pressure increases. So pump at 1 and pressure and condenser low pressure after condenser and Vf. So P1 is already given to us as 7.5 megapascal, and P condenser and Vf we can find this at lower temperature. So are at 50 degrees centigrade from saturated steam table, P of condenser low pressure is equal to 0.012351 megapascal, and Vf is equal to 0.0010121. So all values are given, so put these values here. W of pump is equal to P1 is equal to 7.5 megapascal minus P of condenser lower pressure is 0.012351, and Vf is equal to, this is in megapascal. In megapascal I can write this values as mega, I can write 10 power 3 kilopascal, and kilo is equal to kilo pascal, and pascal is equal to Newton per square meter, and Vf is 0.00125, this is Vf, and cubic meter. So meter square will be cancelled with 2 meter, so kilo Newton meter. So kilo Newton meter is equal to kilojoule. So work of pump will be equal to 7.8476 kilojoule per kilogram. This is meter cube per kg. So this is kg. This is work of pump. Now after pump enthalpy. After pump mean at this point. Enthalpy at this point. In enthalpy at this point. This is H4. After this is pumping. And pumping pressure is increased. So at this point enthalpy is equal to H4 enthalpy is equal to enthalpy of condenser plus work of pump. So enthalpy of condenser at 50 degrees centigrade, this is equal to, this is HF, this is equal to unsaturated vapor line. Enthalpy of condenser is equal to HF, this is equal to HF, and from steam table this is equal to 209.34 kilojoule per kg. So H4 will be equal to, enthalpy of condenser is 209.34 plus 7.8476. So H4 is equal to 216.8276 kilojoule per kilogram, and heat added enclosed feedwater heater. This is closed feedwater heater. So heat added and closed feedwater heater is a enthalpy of feedwater minus H4. So enthalpy of feedwater heater in temperature at feedwater heater is 167.91 degrees centigrade, already determined here. This is 167.91 degrees centigrade. So here enthalpy is 709 kilojoule per kg. 70. At this point, enthalpy HF is equal to 709 kilojoule per kg. So this will be equal to 709 heat added minus 216.824876. So heat added in closed speed water heater will be equal to 492.17 kilojoule per kg. Now we apply mass balance equation on the high pressure turbine. So mass balance equation is equal to m naught mass flow rate into enthalpy of feed water heater minus H4 is equal to y is the mass enter fraction of mass enter into the high pressure turbine, y into m naught into H2 minus H1 dash. Enthalpy enter into the uh, at 0.8, enthalpy at 0.8 megapascal. This is H1 dash and already determined in the start of the problem. So m naught will be cancelled with m naught. Rearrange this equation. Y is equal to HFW minus H4 divided by H2 minus H1. All these values are known to us. So HFW minus H4 is equal to 492.83 and H2 is equal to H2 minus H1 is equal to 18 20.298. All values are given to us, already defined by us. So y is equal to 0.270. This is basically fraction and the extraction and condense in the closed speed water heat extraction from the high pressure turbine. Now this is 1 minus y is the reheat again, mean y is extracted and 1 minus y is a reheat again in the low pressure turbine. So if y is 0.2707 pound mass, so 1 minus y is equal to almost equal to 0.73 pound mass. Now we are finding H2 dash S and S2 dash S. So H2 dash S is the ideal enthalpy at the exit of low pressure turbine. Here this is H2S in the straight, and just like curve is a enthalpy at the exit of low pressure turbine. So here temperature is 50 degrees centigrade. Now H2 dash S and S2 dash S are just only H2 dash S, no need of S2 dash S. So for this we will find X2 dash S. So this is in wet region, so from saturated steam table at pressure is equal to, or here temperature is 50 degrees centigrade, so at temperature is equal to 50 degrees. This is condenser pressure. Here pressure is a temperature is condensing temperature. So here at 50 degrees centigrade HF is equal to 209.34 kilojoule per kg. Hg is equal to 2591.3 kilojoule per kg. SF is equal to 0.7038 kilojoule per kg per kilogram per Kelvin, and Sg is equal to 8.0749 kilojoule per kilogram per kilo. And S2S, here if we check this value, this S2 dash S2S is equal to S1 dash. S2 dash S is equal to S1 dash, and already S1 dash is determined by us. So S2 dash S is equal to S1 dash, because this is straight vertical line and enthalpy is constant. S2 dash S is equal to S1 dash, which is equal to 7.3867. 7.3867. Now S2 dash S is equal to SF plus X2 dash S into Sg minus SF. Rearrange this equation, which is equal to S2 dash S minus SF divided by Sg minus SF. Putting values in this equation, S2 dash S is equal to 0.3867 minus SF is equal to 0.7038 divided by 8.0749, 0.7038. So X2 dash S is equal to 0.91. Now find H2 dash S. Ideal enthalpy at the exit of the low pressure turbine plus Hg minus Hf. All these values are known to us. Hf is equal to 209.34 plus 0.91. This is not plus, this is multiplication. 2591.3 minus 209.34. So H2 dash S is equal to 2376.92 kilojoule per kilogram. Now from H2 dash S we can find this is the ideal enthalpy. Now we can find actual enthalpy from the efficiency of low pressure turbine. Formula from the book of EI-Wakil is H1 dash minus H2 dash divided by H1 dash minus H2 S dash. So this implies that efficiency of low pressure turbine is 0.93. H1 dash is equal to 3099.02, are already found initially. 3099 minus H2 dash is required value, and this is 3099 minus this is 372 2376.92. So only H2 dash is unknown, so find H2 dash, which is equal to 2427.46 kilojoule per kilogram. Now work of low pressure turbine. So work of low pressure turbine is basically H1 minus H2, but here I can write the formula 1 minus Y H1 dash minus H2. 1 minus Y because Y is extracted in the high pressure turbine, so only 1 minus Y is used in the low pressure turbine, so which is equal to 1 minus 0.2707 and 2 H1 dash is 3099 minus H2 dash is 2427.46 kilojoule per kg. So work of low pressure turbine is equal to 456 kilojoule per kilogram, and work of low pressure turbine is more as compared to work of high pressure turbine, because here pressure ratio is more and it depends on the pressure ratio. So total work is equal to work of low pressure turbine plus work of high pressure turbine. So total work will be equal to, previously we found work of high pressure turbine which is equal to 377, and work of low pressure turbine is more as compared to high due to high pressure ratio. This is equal to 833 kilojoule per kg. Now we can find work net because work of turbine and work of pump is now known to us. So net work is equal to work of turbine minus work of pump. So net work is equal to work of turbine is 833 and work of pressure is 6.83. So net work is equal to 826 kilojoule per kg. This is net work. And heat added to the system, heat in the boiler. Now Q of heat high pressure boiler at high Q at high pressure and boiler. So this is equal to H1 minus H1 mean enthalpy at high pressure and H at 0.8 megapascal. H at 0.8 mega enthalpy at which is equal to 2916.36 minus 719. Let I name this HQ1. So Q1 is equal to 2197.36 kilojoule per kilogram. Now Q in low pressure, Q in boiler of low pressure turbine. This is low high pressure turbine, Q in boiler of high pressure turbine, and this is Q of boiler and low pressure. So this is equal to 1 minus y because y is extended here, total is extended here, and now here only 1 minus y is heated at low pressure, h1 dash minus h2. So this is equal to, let I give this name q2, which is equal to 1 minus 0.2707, and this is 3099 minus 2539. These values are already determined by us. So Q2 is equal to 408.19. Now total heat added in the boiler is Q is equal to Q1 plus Q2, which is equal to 2197.36 plus 408.19. So Q is equal to 206.55 kilojoule per kilogram. Now we can easily find cycle efficiency. Cycle efficiency is a net work net divided by heat Qn. So work net is a 826 divided by Qn is 2605.55 and percentage 100%. So multiply by 100%. So cycle efficiency is equal to 31.7%. Now we are finding the work ratio. So formula for work ratio is net work divided by work of turbine. So net work is 826, work of turbine is 833 multiplied by 100. Out of 100 mean percent. So work ratio is equal to 99%. And m dot t, to find m dot t, mass flow rate. So power is equal to m dot t mass flow rate of turbine into work net. So m dot t is equal to power divided by net work. So power is equal to 250 watt megawatt or 250 kilowatt, 250,000 kilowatt, and watt is equal to joule per second. Basically power is given to us is 250 megawatt. We can write this as 250 multiplied by 1000 kilowatt, and watt is equal to joule per second. So this is equal to 250,000 kilojoule per second, and net work is equal to 833 kilojoule per kilogram. This kilojoule will be cancelled. with kilojoule, m dot t is equal to 300 kilogram per second. And this is the end of problem 2.10. And please like and subscribe my YouTube channel and share with your friends. Thank you.